Okay, well, hello. My name is Brian. I'm going to be your instructor for the next 10 weeks. Then we'll be covering a lot of the basic concepts in beginner contest math. The way this class is going to work is that there's going to be a little bit of discussion on, I think, key topics, and we'll be doing a lot of problems. So if you do have any questions, feel free to ask. You can do it through your microphone or through chat. You can message me directly or to everyone. It doesn't matter. Just if you have a question, please ask. The best way to learn is through asking questions. Right. And another housekeeping point, I'm using the free version of Zoom, which means that the meeting ends in 40 minutes. So when that happens and you guys are all kicked off, I just want you guys to just rejoin the meeting. And I'll sort out the logistics of the recordings and stuff later. And speaking of that, the recording of this class will be posted to YouTube sometime like within the next week after the class. So if you do miss a class or there's something that you want to look over, you can always look on the Alphademic YouTube channel. All right, so does anyone have any questions so far? Okay. Well, I guess we'll get started then. So our first topic is on sequences and series. And as you can see here, we'll be covering the topics on the left. And as a warm-up, we have the question, what is the 15th term in this sequence? 1, 4, 7, 10, etc. So I'll give you a few minutes to work on this, and when you solve it, just private message me. All right, so far everyone who's messaged me has the right answer. Okay, the answer was 43. And I guess there are many ways you can do this. I think that one way is just to straight up list it all out. Since 15 isn't very many, you can just do like 1, 4, 7, 10, 13, etc. But this way is kind of slow. And I'm assuming that a lot of you are trying to be taking AIMC 8. And you know that with AIMC contests, speed is very important. So what we want is a more efficient method of tackling this kind of problem. And I think that the best way to do this is through using algebra or just writing each term in a closed form. So I think everyone can see that the first term is 1. The second term is just 1 plus 3. The third term is 1 plus 3 plus 3, and so on. So naturally, we can write that each term in the sequence is 1 plus 3 times some number. Let's call that number x, right? And notice that the first term in the sequence is 1 plus 3 times 0. Second is 1 plus 3 times 1. The third term is 1 plus 3 times 2. So each term is just 1 plus 3 times like the number in the term minus 1. So that means the 15th term in the sequence is just 1 plus 3 times 15 minus 1. And this is equal to 43. And you'll see that this process of pattern recognition is going to be very prevalent in sequence and series just by definition. Yeah. So again, if you do have any questions throughout this presentation, please feel free to ask. But if not, I think we can move on to the first part of the lecture. And that is on just the definitions of arithmetic series. And so arithmetic series are the first type of series that you'll see in these problems where by definition an arithmetic series is just a series where the difference between consecutive terms is the same. So what you just saw before with in a warm-up question, that was an example of an arithmetic series where 1 and then 4 and 7, their difference is always 3. And so this is just one example of an arithmetic series. And on an easier way to understand this, or maybe harder, is if we just put it in terms of variables. So typically we let this first term be A. This is just an arbitrary letter. And this common difference, we usually call it D for difference. So an arithmetic series would always look like A plus D, A plus 2D, and so on. Right? And so again, by definition, you'll see that the nth term that we're looking for, and n is again just an arbitrary number, and 1 is 15. And here it would just be like A plus n minus 1 times D. Since you'll see that the series is 0 indexed, although that's not it's not a term that you need to know. And if my handwriting is illegible, please let me know. Yeah. So another thing that you'll come across is the sum formula for an arithmetic series, and I'll show you 2 ways that you can usually approach adding all the terms. So to give an example, let's say we go back to our warm-up series with 1, 4, 7, and let's say we take the first 5 terms, right? Let's go up to 13. And say you wanted to find the sum of these 5 numbers. Well, first of all, you can just add them. 1 plus 4 is 5, plus 7 is 12, plus 10 is 22, plus 13, you get 35, right? You won't always be able to do this when you have a lot more terms than 5, or the numbers are really big and you might be able to make mistakes. So here I suggest 2 approaches to doing this. The first one is, if you look at this variable expression, you'll see that you can split up each term into the one with the A and the one with the D, right? So if we're adding all n terms, so to speak, of the sequence, you'll have that there are going to be n of the A's at the front, and then you'll have one D here, and then another 2 here, and then so on to get n minus 1 at the last term. So it would just be like the sum of the most basic arithmetic sequence, where the 1 plus 2 plus 3 all the way to n minus 1 times D. And this would be another way that you can see express the sum. And just a key point that if you don't know the closed form to this of 1 plus 2 plus 3 all the way to some number, this is pretty well known. In this case, since it's up to n minus 1, this would just be n minus 1 times n over 2. And the way that this formula is derived will try to tie directly into my second approach, which I think is a bit easier. So I'll get into that a little bit later, as is right now. The second approach for arithmetic series, and I think that is the most efficient one, is to take advantage of the fact that the difference between two terms is always the same. Right? What does that mean? That means that if we use this as an example, if we take the middle term or the average, depending on whether they're odd or even number of terms, no matter how many terms to the right or to the left you go, it's always going to be the same distance away from the middle term. So that means is that if you add corresponding numbers on opposite sides of this middle number, for example, 1 plus 13 is 14, 4 plus 10 is also 14, you'll get 2 times the middle number. And I guess another way to look at it is if we look at A plus D, A plus 2D, A plus 2D is just 2A plus 2D. When we add these two terms next to this middle term. And this is, of course, twice of the center term. And this, by definition, is the average of the three terms. And so you can take advantage of the fact that, again, because the differences between consecutive terms was always the same, the average of any two, the first and last number and the second and second to last number, the average of each of those pairs is always going to be the same. And that average is always going to be the same as the average of the entire sum of every single term. So essentially, the idea is just to find the average or find the middle number and then multiply by the number of terms in the sequence. So for example, 1, 4, 7, 10, 13, the average is 7 since it's the one in the middle. And there are 5 terms that we're taking the sum of. So it's just 7 times 5. And that's equal to 35, as you can see just behind. And this approach is just very fast, very efficient. It's also a lot easier to not mess up. So that I think is the best approach. Are there any questions on just the theory behind it so far? Okay, well, I guess we can move on to a practice problem now. So I'm going to let you guys think about it for like a minute or so, and we can discuss. Okay, I see that a lot of you got it. The answer is not E, but C. And I see that all the answers were either C or E, so I'll try to explain why one is right and one is not. So first of all, you'll see that this problem is from 2016 CMC8. There are many ways to solve this problem. You don't have to use arithmetic series, although I will go over a way that you can use to solve it. The most easy way, I guess, is just to pair up neighboring terms, which I think is the way that is most suggested by how this expression is written. And now, obviously, the difference between all of these are just 2, right? So the real question is just to count how many of these 2's are there that you're adding up. And be careful, because if you notice, these are all even numbers. And there aren't 100 even numbers between 0 and 100. There are only 50, like not including zeros, where you have 2, 4, 6, 8, and 100. Those are only 50 numbers. And since you have 50 numbers, but each of them are paired, that means you only have 25 pairings, each of which add up to 2. So then it's just 25 times 2 equals to 50. A different way that you can solve this, and I guess this would be a good example to how you can add an arithmetic series. You can think of this as the difference of 2 series, with the first one being 4 plus 8 plus 12, and all of this was up order up to 100, and the second one being 2 plus 6, and so on. And when you put it like this, first off, this first method is what I would recommend. But the second one, if you're not entirely sure that your first one is right and you want to see a more concrete example that shows that your number is definitely right, you can first think about what we did to solve, not solve, but what I explained about the average. The average of these terms for 100, average of 4 and 100 is 52. 4 plus 100 over 2 is 52. So this average is 52. And this bottom one's average is going to be 50. Because 2 plus 98 is 100, 100 by 2 is 50. And again, it goes back to counting the number of terms, but this one's pretty easy because 4 is 1 times 4, 100 is 25 times 4, and this is just 1 times 4, 2 times 4, 3 times 4, so then these are 25 terms. And so that means that this answer is just 52 times 25. And using similar reasoning, you can see that these have the same number of terms, so this must also be 25. And you can calculate this out. You can use the distributive property. Either way, the difference is just 50. So do the people who had the wrong answer see what their mistake was? And are there any more questions? All right, well, I guess we can move on to our next section, I think. Okay, I guess now we have another problem. This one I think might take a little bit more time, so I'll give you a few minutes. Okay, well, this problem is a little bit more complicated in that it's not just telling you straightforward what to do, right? So you have to find x, but there's no clear way to find x right now. So I think we can get started on this. A few people do have the right answer here. So the way to do this is to note that you're given that each row and each column, each row and each column is equal to, sorry, not equal to, is an arithmetic sequence. So essentially, if you can calculate the values in either this square, this square, this square, or this square, we can figure out what x is. Because we know the x must be the average of these, the first and last term of their respective arithmetic series. So what this means is that how do we find this term, or this term, or this term, or this term? And you can calculate any pair, but I'll just choose this top one and this bottom one. And recall earlier that this middle term is the average of the two endpoints, or the two first and last numbers in the arithmetic sequence. So this means that 1 and 25, the average is 13, because the sum is 26. And let me clear this up a little bit. The average is 13, so that must be this term right here. Oh my God. And similarly, 17 and 81, what's their average? 17 plus 81 is 98, so their average must be 49. And now, using that same trick once again, x must be the average of 13 and 49. 13 plus 49 is equal to 62. This means that x is equal to 31, 62 over 2. Right, so this problem essentially just shows just how you don't have to know the value of every single term in your arithmetic series. If you're just given two terms and their position, whatever, you can calculate a lot of the things that are related to them. It's just when dealing with them in problems, it's just knowing just their basic definitions and how you can apply them. Right, so were there any questions about how this problem is solved? Okay, well, I guess we can move on to geometric series, which is commonly considered the counterpart to arithmetic series. So what operation is, I guess, different from addition and continues? And this is a rhetorical question. It's multiplication. And so, for example, if we look at series 1, 2, 4, 8, 16, and so on, this is a basic definition of geometric series. And the definition is the common ratio between two consecutive terms is always the same. In this case, it's 2. So we can write this as A as the first term, and then usually we use R for ratio as the common ratio. So the A, AR, AR squared, AR cubed, and so on. Right, and so this is a little bit different in that, okay, the n term, I got that. N term, very similar to arithmetic series, is just a to the r, a times r to the n minus 1. Very simple. The sum formula for geometric series is a little bit different since you don't really have like terms. You know, these AR squared, they're different. These are different like powers of r, so you can't just directly add them. And the idea is that if we take this sum of all these terms and multiply by r, so let this be s, right? S times r is equal to AR plus AR squared plus so on until you get to AR to the n. So you see that when you multiply by r, there's a lot of overlapping terms. It's just this a and this a times RTN are different. And so if you subtract them, so you can do this in either way. I'll just subtract the first one from the second one, since in this case it's increasing. R minus 1 by the distributive property, R minus 1 times S is equal to A times R to the N minus 1. Because RTN is right here. This is a 1 next to the A. So those are the only terms left. Everything in the middle just cancels out. And you can just divide both sides and get S equals A times R to the N minus 1 over R minus 1. And so the main idea is that you'll see that the sum is just the next term, A to the R to the N, A times R to the N, minus the first term. So this is the next term, this is the first term, and then divided by R minus 1. And so you don't really have to remember this exact formula, just remember this concept of multiplying by R, because I think that's the most important step in this process. And lastly, for infinite series, this is the most common, I think, when you see geometric series being represented, is when you have something like 1 plus 1/2 plus 1/4. The common ratio is smaller than 1. So the series is always decreasing until it will eventually reach 0 at infinity. And the idea behind this kind of infinite series is that it will always converge to some finite value. And you can use a similar approach to this that we use for a finite number of terms, but when you extend it to infinity, what happens is that the formula will just be A over 1 minus R, or minus A over R minus 1. Because essentially what happens is that since R is less than 1, it has to be less than 1, or else the series will increase infinitely and will never reach a finite value. That's why R has to be less than 1. So when that happens, R to n as n approaches infinity becomes 0. If you think about it, these terms getting smaller and smaller, so eventually it'll be so small it's basically negligible, and just consider that 0. Then this R to n minus 1 term just becomes minus 1, and so it's minus 1 times A over R minus 1. You can factor out the minus 1 and be left with this. This is a formula that I would recommend remembering. It comes up a lot and is overall very important. So for example, if we use this example I brought up, 1 plus 1/2 plus 1/4 and so on, A is 1, R is 1/2. So this is equal to 1 over 1 minus 1/2, and that's equal to 2. And that is indeed true. So yeah, that I think is about it for geometric series. Are there any questions so far? Okay, well, let's move on. So very, very similar to what I just did, actually. So this shouldn't take too long. I'll give you guys a minute. Okay, well, we're actually kind of running out of time. Not like running out of time, but the answer is 4. You can use this formula. You can also use the fact that I already calculated the entire right section of the expression. So you'll see that just adding 2 to 2 equals 4. All right, very soon this meeting is going to end. So I want everyone to rejoin after they're kicked out. Okay. We're just waiting for that to happen at this point. All right, well, I think that we can discuss the answer to this problem. It's 3279, and if we go back to the earlier, oh shoot, I don't have it written. Never mind. I'll just say it. If we go back to what we learned earlier, it's that it's equal to the first term, or sorry, the next term minus the first term over like 3 r minus 1. R here is 3, since the common ratio between 9 and 3 is 3, 27, 9 is 3, etc. So it's going to be looking like this, right? And the next term, 2187, this is equal to 3 to the 7th. So the next term would be 3 to the 8th. And so this is simply our answer. This is straight from the formula. So yeah. Now, let's go on to our next one, which is recursion. And I'll be honest, this one I think is one of the more sketchy topics, and I don't know how, I'm not entirely sure how completely necessary it is, but I think it's just good to know when it does fall under sequences and series. So I think that the most commonly known recursive sequence is the Fibonacci sequence, 1, 1, 2, and so on. 2, 3, 5, 8, 11, 13, where each term is just the sum of the 2 terms before it. Right. So this is what we call a recursive series, where it follows a recursive formula. So it's kind of like an arithmetic sequence, and it's kind of like a geometric sequence, in that there is some rule for the next term, but this rule varies a lot. And so, for example, for this formula, you can just say that this next term, let's just denote a sub n as arbitrary nth term, this equal to the term before it. This, the sum of terms before it. And this is what we call a recursive formula. All it does is describe how to get the next term from what you have previously. It doesn't have to have 2 terms. It can have 3, it can have 5, it can have 1. It doesn't matter. This is just a very general kind of broad term for any kind of series that fits this description. and you'll see that I think the name recursion or recursive formula, it kind of describes how you can like find every term in the sequence by starting with the base terms and then repeatedly applying the same formula to 1 and 1 you get 2, 1 plus 2 you get 3, 2 you get 5, and so on. And so I think this is really all you need to know about recursion. It's just by definition this. Recursive formulas are something you'll probably see in a little bit beyond MCA level. But it does have some uses in telescoping, which we'll go over later. Okay. So we have this question. I'm not going to have you try it because it's really just guess and check. You'll just see that the recursive formula is this. I'm not going to admit it. It's literally in the presentation. And what I want you to get away from this is simply that this kind of idea does exist, and there are some offshoots of this that you'll probably go into later in your math career, and also just verify that this formula works and it makes sense. So recursive formula here is a sub n is equal to 2 times a sub n minus 1 plus a sub n minus 2. So the original 2 terms, twice the original or the one right before it plus 1 times the one 2 times before. So 8 is 3 times 2 plus 2. 19 is 8 times 2 plus 3, and so on. Again, you probably won't see this kind of problem because unless they give you the formula, it's quite guess and check oriented. Next, I want to talk about telescoping because I think telescoping is definitely within the realm of this course. And essentially, the idea behind telescoping is that you take this complicated expression and you narrow it down by like deleting all the middle terms. So think about when we were doing the geometric series sum, where by multiplying by s, you could cancel all the middle terms because they were all the same. And this is kind of similar to how telescoping works. So I guess the basic example of this would be like, let's say have the sum by 1. So let's say you want to find like 2 minus 1 plus 3 minus, I don't know why we want to do this, but you can. 2 minus 1 plus 3 minus 2 plus 4 minus 3, and so on, right? Let's say we want to go to like 100 minus 99. So what happens is that for one, you can just calculate. This is just ones across the board, so that makes it pretty easy. But another way that you can look at it is through telescoping. So with telescoping, what it means is that you cancel all the middle terms. And the idea is that this minus 1 doesn't have counterparts, so we leave it in the final sum. But there's this 2 and the minus 2, they cancel out. The 3 and the minus 3 here cancel out. And there's going to be like a 4 and a minus 4 next term somewhere here that cancel out. And eventually what happens is that all the terms cancel out except for this minus 1 and this plus 100. So the final sum would be 100 minus 1 or 99. So the idea is to look for ways to take this really long sequence that you can't, like this one you can, but a lot of ones you can't normally just sum by hand and just do it like this. And as you'll see in examples, it doesn't just apply to addition and subtraction. I think that telescoping is best learned through the examples because that's where the concept, I think, really makes sense. So let's go on to this problem. This is a problem 2, but I think it serves its purpose quite well. So why don't we take a few minutes to look at this problem, just try to solve it. All right, so far I'm getting some mixed results. But, okay, well, I think that a little bit more than half of you are right. It's D. And with this problem, since there aren't really that many terms, you can just straight up just write it all out. So 1 plus 1 over 1 is 2. 1 plus 1 half is 3 halves. 1 plus 1 third is 4 over 3. 1 plus 1 fourth is 5 over 4. 1 plus 1 fifth is 6 over 5. And 1 plus 1 sixth is 7 over 6. Right, and these are all being multiplied together. So I think that this is pretty easy to look at now. You can just, this demonstrates the power of telescoping. Instead of multiplying the top, multiplying the bottom, you can just say, well, this 2 on the top and the 2 on the bottom, they cancel out. Same with the 3s, same with the 4s, same with the 5s, and same with the 6s. And so all that's left is 7. And that's the answer. So I hope everyone can see here that the main idea is to just do as little work as possible, because in the long run, it's going to save you a lot of time. So, and it's not necessarily even the bad decision either. So yeah, are there any questions on this? And if you did get it wrong, do you understand how it was wrong? All right, well, if not, I think we move on to a little bit more difficult version of telescoping, which is, I guess we're not, okay, it's this. It's not this. It's this. That's the one I want to go over. Okay, well, I just showed the answer. Okay, well, it's fine. I wanted to go over this problem anyway. Find the sum of this. So first off, these are a lot of fractions, so you can't just sum the denominators. And what can we do? First thing to do is let's say we write it out, right? And you'll see that this gets pretty complicated pretty fast, since you don't really have many, you don't feel to find like a big common denominator, simply because you're going to have factors of every single number denominator, and it's not feasible to brute force this problem, since you'll straight up just not have the time or the calculating capacity to solve this. So what you have to do is you have to look for shortcuts. And with this question, you'll see that questions of this form usually indicate that you should be looking for telescoping, because that's really the only kind of path you can take. And so, like, what kind of expression would we want for a telescoping to work? It would probably be expressing individual terms as a difference of two terms, so that when we add them up with all these other terms, you get some cancellations and it becomes a bit easier. And so I think naturally the first thing to try is just 1 over this first number minus 1 over the second number, right? I think that is what you guys should probably try first, and it actually does work. So for example, 1 over 1 minus 1/2 is 1/2. 1 over 2 1/2 minus 1/3 is 1/6. And if you keep going on this, it works everything. And this is because if we look at the general term, 1 over n and 1 over n plus 1, take the common denominator, this n plus 1 goes to the top, this n goes to the other side. So this is n plus 1 over n times n plus 1 minus n over n times n plus 1. And so these have the same denominators, so you can just add the numerators. N minus 1, n plus 1 minus n is just 1, right? So this just becomes 1 over n times n plus 1. So now we do have a way to break up this question. So now it's not just 1/2 plus 1/6 plus 1/12, it's just 1 minus 1/2 plus 1/2 plus 1/3 plus 1/3 minus 1/4, and so on until you get to 1 over 100. Sorry, 1 over 99 minus 1 over 100. And you'll see this minus 1/2 cancels the positive 1/2, a minus 1/3 cancels the positive 1/3, and this will keep on going until you cancel this 1 over 99. And all that's left is 1 minus 1 over 100, or 99 over 100. So I think this was probably the most complicated one yet. So if you do feel confused, please ask. I'm willing to help and stuff. So yeah. All right, well, even if you don't understand, again, you can rewatch this recording on YouTube when it does come out. So look forward to it. All right, let's go back to the problem I did skip over, which is not all. Useful formulas. I think I already went over the useful formulas in the other sections, so that's why I'm skipping over it. So I actually showed the answer here. That's fine. You can still try to figure out this method. And as you saw, this is the last problem, so we have about 7 minutes to figure this out. Well, I guess since you guys know the answer, I think that you can just private message me and like maybe your ideas about the method of how to solve the problem. All right, I think I'm gonna start to go over this. So recall earlier, this doesn't say directly, but the sum of 25 consecutive even integers. So what should this immediately remind you of that we learned about today? Okay, put it another way. Of the sequences that we learned about today, or the techniques, what does this align with the most? What kind of sequence is this? You guys can feel free to say something. It's not a trick question. All right. Well, no one said anything yet, but I'll say it. This is an arithmetic series. This is because the word consecutive means that the difference between each integer that we're adding up is equal to 2, right? And since this common difference is the same, it must be an arithmetic series. And now, like we talked earlier about the sum of an arithmetic series, right? And the few ways to go about it, and the main one that I mentioned is using the average or the middle term. So I think it's pretty clear that since the sum is 10,000 and there are 25 terms, the average must be just 10,000 divided by 25 from the reasoning that I used earlier. And so this is 400. So this tells us that the middle of the string of consecutive even integers is 400. So that means that this is the 13th term, because the average of 1 and 25 is 13. 13 is like the median of the numbers. That's why it's the 13th term. That means that there are 12 terms on to the right or larger than it, and 12 terms smaller than it. And we're asked for the largest of these integers. So this means that we need the 25th term. And so there are 12 terms here. So the easiest way to do this is just to add the difference, which is 2, 12 times. Because by definition of the arithmetic series, the consecutive terms will differ by 2. So in order to get 12 terms after 400, just add 2 12 times. And so the sum is 424. All right, so that was the last problem. If you do have any questions on this, please do speak up. This class is meant to be for everyone to improve on their math skills. So if you do feel that there's something you don't know, please do ask. I beg. But yeah, that is kind of it for this week. Like 424 is the answer. That's all. And today we covered this stuff. We covered these. So if you guys have any questions, you can ask. If not, the lecture recording will be posted later this week. And I'll see you next time, I guess. So. Have a good day, everyone.
Thank you. Bye.